Okay, today we're going to look at what happens when gases are mixed together, and basically what happens when it's not just oxygen or it's not just chlorine gas, what happens when they're put together. So up until this point, we've looked at one thing, like there's oxygen gas. Now we're going to look at what happens when there's oxygen and nitrogen gas. So what happens is there's a guy, if you remember, John Dalton. He was a good chem teacher. He was talked about the atom, and he came up with the billiard ball model. And he studied gases, and he came up with the fact that if you just add up each of the individual gases' pressures, you can get what's called the overall total pressure. So if you have a mixture of nitrogen and oxygen, and say your nitrogen's 3 atmospheres and your nitrogen's 4 atmospheres, what he said was those individual things were called the partial pressure because they're part of the total pressure, and then when you add them up, you would get the total pressure overall. So remember, gases just kind of think they're all alone, they act individually, and they just act independently. Sorry about that. All right. So we have this here. We have a mixture. We have 65.04. So we have these two mixtures of gases, and we want to just kind of figure out what's the partial pressure of each one, and then what's the total pressure. So what we're going to do is just treat them like they're completely unique, and then look at them individually, and then we put them together. So if we look at this for, helium, we don't know the pressure. That's what we're looking for. So we know it's in a 6.50 liter vessel. They told us it was 65.04 grams. So what I did is I looked up the molar mass of helium, and that's 4, and I converted my grams to moles, and that's where I got my 16.26 moles. And then I didn't have to, I could choose whichever R we wanted, but I like atmospheres, so I picked 0.0821. And then the last thing I did is I converted my 13 degrees Celsius into Kelvin. So I solved for that, PV equals nRT, solved for P, and I got, with sig figs, 59 atmospheres. So this helium, there's a lot of helium, and it's exerting a lot of pressure, and it's 59 atmospheres. So now we're going to do the same thing for chlorine. And you can see we still didn't know the pressure because we're looking for the pressure of chlorine. It's in the same vessel, so it's 6.5 liters. They told us it was 13.5 grams of chlorine. Be careful, chlorine is Cl2 because of Bringelhoff, because it's by itself. So I looked up the molar mass, I turned it into moles, and it's 0.3803 moles. Use the same R, use the same temperature. And this guy, there's not that much chlorine, and he's only exerting 1.4 atmospheres. So helium's partial pressure is 59 atmospheres. Chlorine's partial pressure is 1.4 atmospheres. And then when we look at the total pressure overall, we add them up, and with sig figs, it's 60 atmospheres. Another way you can look at things is with mole fractions. Remember, moles kind of equals everything out. You can look at things much better than just like a mass. So what you do is you X, the little X is for a mole fraction, and what you actually do is you figure out how many moles you have, and then out of how many total moles you have, because that's the way you compare things. And you can actually get the partial pressure from that. So if we look at the next page, apparently we went to Saturn's moon again, Titan, and they said that when on the surface, there's 1,220 torr of pressure. And what they said then was also that the atmosphere is a mixture of gases, and there's 82 mole percent of nitrogen, 12 mole percent of argon, and 6 mole percent of methane. And we want to know, okay, how much methane is there, how much argon is there, how much nitrogen is there. So what we're going to do is just figure that out. So if I want the pressure of nitrogen, they told me it was 82%, which mathematically is 0.82, and I just multiply that by my total, and that means there's that much pressure of nitrogen on the surface of Saturn's largest moon. And then what I do is I just keep doing that for all of my different things. So if I do argon, argon's 12%, or 0.12, times the total pressure, which is 1,220 torr, and that gives us 146.4 torr for argon, clearly a little bit less. And then the last guy, for methane, he's really small. He's only 6%, or 0.06. So I multiply him by the total, and he's 73.2 torr. And if you add those all up, you should get the 1220 all over again. All right, the last thing we have to look at is what happens when you collect gases over water. So remember, if you're making a gas in the lab, which we will do as soon as next week, they're kind of hard to catch because they do like to escape. So a lot of times, most of the time, they're going to bubble the gas through water. And basically, whenever you bubble something through water, you catch some water vapor. And the higher your temperature, the more that there's going to be, the more water vapor there's going to be. So if you look at the very end of your note packet, there is a chart that tells you how much water vapor there is at different temperatures. Usually, I'll tell you it to you on the AP test. Usually they tell you, but you just need to recognize that you have to subtract that water vapor out first. So what we're going to do is we're going to look at two problems. That's it. First one's really simple. Second one's kind of putting everything together we've done, and then just kind of seeing what does it look like. So first one. We made oxygen gas when we heated KClO3, and they collected it over water. They tell us the total volume is 150 milliliters, they tell us our temperature, and they tell us 810 torr. All we want is the partial pressure of oxygen gas, and they tell us the partial pressure of the water. So what we need to think about is we have the total pressure that we caught, P total. That's going to equal the pressure of our oxygen plus the pressure of our water vapor. So all we have to do, that's all it's asking us for, is just subtracting out that water vapor. So our total pressure, they told us, is 810 torr. We don't know the pressure of our oxygen. That's what we're solving for. And they're telling us that the pressure of the water is 22.4 torr. You could look this up on that chart. If the pressures didn't match, you would convert them so that they would match. But then all you have to do is just solve for that X, and you can figure out what pressure is actually from the oxygen. And that's kind of what you do. Now, usually, this is not the whole problem. It can be, but it's usually not. So what we're going to look at in the next one is a big problem, including this, and then we're going to be done. All right, so last one. This one we actually have an equation. So they tell us ammonium nitrite, which is NH4NO2, is going to decompose to form nitrogen gas and water. So we get N2 and we get two waters. So they decompose it. We get 511 milliliters of nitrogen. They collect it over water. That's kind of your clue. Over water. At 26 degrees Celsius, 745 torr total, and they want to know how many grams were decomposed. Well, the decomposed is that ammonium nitrate, so we're going to have to go all the way back to that. And they're telling us the water vapor is 25.2 torr. So the first thing we have to do is subtract out the water vapor. So the first thing we're going to do is get rid of water. So what I did is I said I have 745 torr, that's my total pressure, and I'm going to subtract out the water vapor. And I get 719.8 torr of just nitrogen gas. So that's my pressure of my nitrogen. The next thing I have to do is, since I want to go backwards, I want to go from nitrogen to ammonium nitrite, that would mean I would need to use stoich. Well, I can't do stoichiometry with a pressure. That doesn't make sense. So the second thing I have to do is use my ideal gas law to figure out, okay, if I have 719.8 torr of nitrogen under these conditions, how many moles is it? So I use my ideal gas law, PV equals nRT. This is messy, and I apologize. So my volume is 0.511 liters. Sorry about that. So you didn't know, but I had to go somewhere. So we're at the ideal gas law, and you just want to make sure the only thing you have to be careful of is our pressure that we figured out, 719.8 torrs. We don't have an R that goes along with that, so we had to convert it to atmospheres or kPAs. I chose atmospheres. Apparently I enjoy atmospheres more. And then I plugged it in, and I got my moles of nitrogen. But if we look at the question is how many grams of the thing we started with were decomposed. So the very last step, I know this is nasty, is a Stoich problem. So we start with how many moles of nitrogen we have, which we figured out was 0.0197. We do a Stoich mole ratio from nitrogen to that ammonium nitrite. And then we look up and say, how heavy is that ammonium nitrate? That's 64.0 grams. And it turns out for this all to happen, for us to collect that amount of nitrogen gas over water, it means we started with 1.26 grams of that ammonium nitrite. So this is kind of one where you can see everything put together.